Okay, problem 2 seems to have clogged up my computer because I didn't save as an 04. So we're going to look at here another basic form of problem. This is not a cantilever connection, but it's something with a single pin joint and then a cable. This basically, cable means you know the direction but not the magnitude of the reaction force there. This is tying down. Very often the cable's tying down and the cable's giving you the geometry. So remember, and we're going to do the solve for the reactions here because what's behind this is not important, but solving for the reactions always is. So I'm going to go ahead and realize that we should have 1, 2, 3, 4, 5, 6. If you think about this reaction force here being in effect a force with both in the x and the y direction. So I'm going to double click in here, and then I'm going to go do one more add. I'm going to grab across here. I'm going to edit, copy, and then as I'm looking in the equation editor, not bad once you get used to it, but not something you want to master to start, but not bad. File, especially as you decide that there's going to be pieces of this. I'm going to pull this down a little bit here. There's going to be pieces of this that you're going to realize very soon it'll be handwriting recognition. So when you do an integral, you'll know an integral. So let me leave the reactions last. Remember how I take myself over there. 0, 5, 1.31, 3.28. Remember, we could just as easily, and I think it's probably true that you will do it, and I'm going to remember here that if I put over the top here and click on it, that pops up. That's a pretty nice bit. And I'm going to go ahead and try to get some of this organized a little bit better within here. And I'm going to say 0, 5, 1.31, which is in the x direction, and minus 3.28. So in all reality, you go ahead and you solve for your actions kind of the same ways you do before, but now everything's in front of you, nothing's behind you. You need to kind of equate with all the forces, but in this case we're going to write some of the forces, some of the moments about the initial point 0, 0, which you'll see later is where our reaction is. So we've got the first one done. We can click over to an escape bar over here. Click to the second one. It is 2.5 and 5. That's, in fact, when you realize how systematic the data is, that's why you start to do things like data extractions. But you kind of have to be very aware, as many of you know, what your coordinate system is and anything else. That's 0.90 if you think about it, and minus 2.52. You can start to see the potential for transcription errors coming in here. You've got that one done. We can click over to here, escape out. Grab that one. That's my third force, 5 and 5. Let's try to remember that if we put this in the right spot over here on our computer, we don't erase it when we go over here. 5, 5, 2.60, and minus 1.50. Some of you may be realizing it's just as easy to stick it in a spreadsheet. I do want you to see the determinant here, or sticking it in your calculator with a 0 for the z force and a 0 for the z and the radial vector. It would also be a good idea. So we've got 3 of them done. In other words, we have the 3 applied forces. Now I'm going to do the base of reactive forces, and realize you do first I'll do the ones at the 0, 0, and then I'll do here, and I'll show it as a 1 unit vector. A 1 unit vector. But in reality, that unit vector is going to have some components to it, won't it? Because that unit vector is going to have some x and some y, the delta there, and so that's going to be basically something we can do any number of ways, but I'll start with this. You know that this is, the first one is 0, 0, and this is an all reaction. You can do those 2 ways. We only have to do them once. This is reaction at A in the x, and this is reaction at A in the y. So you really don't need to have that stored in 2 places. They're both there. That is basically the components of the torque, and again we're talking about through 0, 0 there, so you're generally okay. And another way to write this would be 0, 0, reaction A in the x, putting that as 0. I'm going to go undo here. Wrong way to undo here. So 0, 0, 0, 0, and then 0, 0, 0, R, A, and the Y. So you don't necessarily, you can do them together or apart. And then finally here, if you think about this one, we grab it, it's 0, 2.5. And then minus 9.22. And minus 0.39. Minus 0.39. Now you've got all this laid out. It's all there. The fact is, however, that these numbers here are unsolved, as in all reality are these, right? So these are actually not correct. You're going to need to multiply these numbers out, so you can actually take that number and think about it. That's there is actually times the reaction at A, reaction at B, and these will be also times the reaction at B. So the reality is we don't know that, we do know the general direction of the reaction at B, and therefore that's how we can do this mathematics. What you're essentially doing is realizing the torque here, and I will do it here in a second. The torque due to these three forces should be equal to the same thing as that force, and I'm going to lay it in here, a line from the end point of here perpendicular to that. So the sum of these forces are going to be that force times that distance. And now I'm going to go ahead and think about basically 1, 2, 3 are going to have values, and this is going to be a reverse value in terms of its magnitude, and I will check it within here. I'm going to pause to do that. Remember, this times this plus this times this plus this times this is going to be reacted to by basically these right down here, and then these will solve. And so what you'll see when you come back then are the reactions solved, and then we'll start the concept of what's behind this is not important. Okay, when you add up the sum of the moments of this force, and this force, you get a negative 28.81. This has to react to it at a distance of 2.13, and so you get a reaction in the end of, as is drafted here, 12.47. All right, so this numbers down here become, in fact, this, because you've now determined the reaction. We're going to done with that, more or less. We're going to go try to get to the review, start inking, review, stop inking, pens, close ink tools. So now you're within here, and you realize that this now is 12.47. So this is determinant of this, but not so much that it's x is minus 11.51. So your x is minus 11.51, and then your y is minus 4.81. So now you have everything, if you would, solve except for the reaction A and X, and we'll go ahead and fill that out and begin then on what's behind this is not important. So I'll see it. This will have these solved out in a second. You can actually do that by changing your rotation point to any point here, and this wouldn't be a bad one to do it. That would get you your value of reaction about this point, would get you the value for the reaction in the x direction. And then in the end, if you wanted to really take it to the extreme, you would take a line right out here, and then this force and this force would not be concurrent. You could write the sum of the forces about those three, and that you get your reaction in the y. So we're going to end up here just showing you in the end, before we start this next book, what the reaction at F and the X, reaction at A and the X and A at B, or A and the Y is going to be, and begin from there. We'll pause here. Okay, when you're left with just two forces left, you can actually sum. You don't need to slide the vectors. You could slide them all around and you come up with that reaction. So right there, you see this problem now. He writes that out with the reactions stored. Those reactions are then quantified in this set of matrices to the right, and with that we will do what's behind us is not important. Thanks for listening, and stay tuned for the next one.